So the animation window over here shows a simulation of the motion of electrons in a wire. The electrons are the green dots, and the wire is this red bar here. When you first open this code, you'll want to scroll down to line 122, because this is the part where you change things to set up your little experiment. The first 121 lines are all things that just set up the wire and the electrons based on your specification. So you shouldn't need to change anything above there unless you need to get under the hood and make some changes to how the code actually runs. So the first thing I want to show you is how you make this wire. Basically, that's the thing you control, is the properties of this wire. So you do that using the makeWire function. It takes quite a few arguments because there's quite a few things you can specify about this wire. First, you give the wire's position. We're going to start out with a wire centered at the origin. That's just the easiest thing to do. You give the wire a length and a width. So length is the direction along which the current's going to be flowing, and then the width is just the width of this square cross-sectional area that you see the electrons heading toward down here. Then you specify the direction. That's simple up, down, left, or right. Here we've got direction set to right, and that's a literal string of right. Then you have the resistivity. Resistivity is how difficult it is to get electrons to flow through the wire. We'll take a look at how that mechanism works in a minute. Then you specify the electron density. So how many electrons per cubic meter are there in this wire? That's usually a very big number in real life samples. We're just making that density 5 for simplicity so we can actually see the electrons. And then you specify the voltage across the wire. So we're imagining that this is part of a circuit. We're not showing the battery here, but basically this is the amount of voltage that we are applying across the wire here. And then you give the wire a color. Notice that this is the color that shows up on the wire. It's also the matching color that shows up here in the current graph. So this is showing the current that's going through the wire. You can see it's pretty consistent. It's jumping up and down because the current is literally counting the number of electrons passing through the center of the wire. So it's going to jump basically every time an electron passes through the center, and then it's going to decay when there aren't electrons passing through the center. But with enough electrons in the wire, it makes a pretty flat curve. You can get a decent reading off of it, at least for demonstration's sake. And so if you wanted to make another wire, I have a note to myself here to show you how to create a wire. All you'd have to do would be to copy this section here. Let's do copy and paste. I suppose I should also specify the voltage and direction here. Paste, there we go. And then you just change the values that you want to play around with. So let's do a simple one. Let's suppose I take an identical wire and I ramp its voltage from 5 up to 10. And let's separate these wires a little bit. Let's move this wire up by, let's say, 3 units. And so if I run this, oh, and I need to give a different color, don't I? Let's give you a color of, let's make this one green. There we go. So we'll have a red wire and a green wire. So the wires are identical. The only difference is that the green wire has more voltage applied to it. And so you can see I've got the same length, the same width for these wires. I've got the same electron density, even though the electrons are in different places because their locations are randomly distributed. They've got the same density. You can kind of, count the same number of electrons per segment in the wire. The only difference is the voltage in the green wire is bigger, which means its electric field is larger. So this arrow in the middle represents the electric field across the wire. And as you probably have learned at this point in your physics class, electrons are always going to be accelerated opposite the direction of the electric field. So that's why they're tending to move to the left while the arrow points to the right. And then after the code has run for a time of 20, we'll call it 20 seconds. It's not 20 seconds in real life. Then it creates the current graph. Basically, if you create the current graph too soon, it's going to jump up and down a whole lot. It's not going to really give you a nice looking graph. So we just wait about a time of 20. You could adjust that wait time if you wanted to display the current graph. But what you can see, we've got the current in the green wire and the current in the red wire, and you can immediately see that the current in the green wire is higher, which makes sense, right? We applied a higher voltage. Higher voltage should give you higher current. That's what Ohm's law basically says. And in particular, remember we doubled the voltage. We went from a voltage of 5 in the red to a voltage of 10 in the green. and you look at the current, it's pretty much doubled. It's hard to do a direct comparison since they're varying so much, but this thing is 2 and a little bit, and this green one is 4 and a little bit more. So we've actually got a pretty good demonstration of Ohm's law right away, right here in our simulation. So now that I've shown you how you interact with this code, because the only thing you have to do is change the stuff about the wire, let me show you how this works. So we're simulating the motion of these electrons in a wire, and you notice that they're not traveling in a straight line the entire time. You notice that they're kind of bouncing around. Basically, they are colliding with the atoms, the nuclei that make up these wires. Now, I'm not showing the atoms because that would take a lot of simulation time and a lot of simulation power to add in. But what we're doing is we're basically scattering them randomly. Let me show you how we do that. This is all taken care of in this function move electrons. So this is where we're applying the Euler-Cromer method, which you should be familiar with by now if you're doing this level of coding, but if not, I'll have a link about Euler-Cromer in the description below. Basically, we look over every electron that we have stored. So when we create these wires, we add their electrons to this list called electron list. So E here represents each individual electron in turn. We first pick out which wire the electron is in, because we need to know, which electric field it's experiencing, which resistivity it's experiencing. And here in line 81 is where we figure out whether the electron is going to scatter. Scatter just means it collides with an atom in the wire. And so we pick a random number between 0 and 1. And if that value is less than this fraction, then we do have a scattering event. We do have a collision. Now, the way this collision is set up, it's our time step dt divided by the wire's scattering time. So scattering time is this notion in this kind of classical model of electrons in a wire, that it's the average amount of time that it takes for an electron to go between collisions. So if you think about you're an electron and you just had a collision, what's the average amount of time you can expect to travel freely before you have another collision? And so when you set up this fraction, you're basically setting up the probability that you have a collision. So the bigger the scattering time, the less likely you are to have a collision. The smaller the scattering time, the more likely you are to have a collision. And so if we're scattered, then we have to randomly reset the electron's velocity. So first we pick a random angle between 0 and 2 pi. So we're going to scatter in a random direction here in the xy plane. And then we just reset the electron's velocity to be the electron speed, so that's going to be a constant. This resetting speed, you could vary that in the model if you wanted to. And then we set up the vector here. Now we're not scattering in the z direction. You can add that in if you'd like to. If you look at them, you'll notice that they're only scattering in the x and y direction. Nothing happens to them in the z direction. You could change this so that they do scatter in the z direction. You just need another random angle. It's not that difficult to do, but I leave it to you as something to try. Now, if they don't get scattered, if the velocity isn't reset, then it's free to move under the influence of the electric field, which is where we have the velocity update. Now, remember, electrons move opposite the electric field, so we have a negative on here instead of the usual positive to add on our force times dt. And here we've got electric field times dt. So we're leaving off the charge here. We're just using units of 1 for the charge. So you could add in real units for the electron charge here, but then you'd also have to use real units for the density and for resistivity. So you'd have to update basically all the numbers. So really, this electric field is more like the charge times the field, but you get the idea. It's basically the same thing. Now we then have one other piece to this. Remember, these electrons need somewhere to go. So if you just let this code run, if that was the only part you had, the electrons would be crowding out over on one side. So I've set it up where for these wires, the electrons loop around to the other side. So for example, if you watch the red electron here, I have one of them marked in red just so that it's easier to keep track of one of them. When this electron reaches the left edge, it's going to bounce back over to the right edge. Now, it might take a little while because you can see, even though we've got an electric field and we've got a nice current, these electrons aren't moving terribly quickly on their own, which is a hint to an answer to one of the questions at the end of this video. But basically, we check for whether an electron has reached the edge of the wire, and then we just send it over to the other side. That's basically what we're doing in this block of code here. I'm waiting to see if this red one reaches the edge. I keep waiting for it. You'll see it pop over on the other side as soon as I look away, I'm sure. So that's what we're doing over here. Basically, we're checking to see if we need to pop an electron over to the other side. And then down here is where we're calculating the current. And basically, current is charge per time, right? And we're not really worried about the absolute units for the charge. So we're not worried about whether it's a charge of 1 or a charge of 1.6 times 10 to the negative 19. Really what we're just looking at is counting the number of electrons that pass through the wire. There, you can see a couple of them disappearing over here on this side. I'm waiting for the red one to get over there. And pop, there he goes. He popped over to the right side. That's what's happening up here when we move it over to the other side. All right, good. We can move on now. So basically over here, we're checking for whether the electron has passed through the center of the wire. We're just kind of taking that as a spot where we have our ammeter, our current measure, and now it's popping all over the place left and right. And once we have that, we just add that electron, we basically add that count to the average current that's going through the wire here. Now you notice the way we're calculating it is as the dot product of the electron's velocity with the axis of the wire, and pop, there it goes again. And so basically that keeps track of whether a current's going, or excuse me, whether an electron is going against the direction of electric field or with the direction of electric field. So we want to count current as electrons going this way, not electrons going this way. So electrons going back this way would count against our current. So again, that's why we have this thing, jumping up and down. And so basically, when we come down here to our time loop, we're running this move electrons once per frame, and then we're adding to the graph here. So we've kind of separated out the animation here from the actual, or the animation loop here from the actual physics crunching up above. So anyway, I hope you find this a useful simulation to help you understand how to connect the motion of electrons in a wire with the actual circuit behavior. There's a number of activities for you to do at the end of this video so that you can further explore these relationships and visualize this. So thank you so much for watching. I will see you next time. Bye-bye.